course for AP Calculus on the topic of slope fields. So slope fields are a graphical representation of the general solution to a differential equation with different c values. Remember, a particular solution is when you know what the specific constant is. General is when you don't. So to draw a slope field for the given differential equation, here's your differential equation, at the points indicated on the graph, so all these points right here, and set up a little table of information here. And usually the easiest thing to start with here is to substitute in what would make the numerator and the denominator 0. So what would make them both 0? If x is 0 and y is 0. Well, if you get 0 over 0, that's what's called indeterminate. Divided by 0. Because what times 0 gives you 0? Well, there's a whole bunch of different things. You can't determine what that is. So at the point 0, 0, they actually don't draw anything. So what you can do to remind yourself you don't draw anything, like an open circle there, so there's nothing. We'll see what that means over there. Well, let's see what happens if the numerator is 0, which is when x is 0, and the denominator is not 0. Well, then you get 0 over some number that's not 0. Well, that would be 0. When you have 0, that's when you have slope of 0, that's horizontal. Okay. And what we're drawing here, so when x is 0, y is not 0, so I'm right there with these 4 points. We'll draw a horizontal tangent line. And what we're really drawing, the slope field is made up of like mini tangent lines. So, right here. And it doesn't matter how long you draw, just don't draw it too long so that it interferes with the other. So those 4 points, tangent line would be horizontal. The slope is 0. And let's look at the other way around. What if x was not 0, so the numerator is not 0, and the denominator is 0? Well, then you get some number over 0. That's called undefined. An undefined slope is when you have a vertical. So at the points where the y coordinate is 0 and x is not 0, so with y equals 0, you have vertical tangents. So, and the slope field is made up of a bunch of mini tangents. So what this is showing you is if the graph were to go through these points, these would be the tangent lines. So what's going to give us when we put it all together is kind of the general shape of what these graphs look like. Now, we've taken care of those, what makes the derivative 0 and undefined. Now we can try to fill in all the other ones. Usually I think it's easiest to start in your first quadrant. So let's say we plug in the point 1, 1 for x, 1 for y. Well, that would give you negative 1 over 1, so that would be a slope of negative 1. So at the point 1, 1, draw yourself a tangent line that looks like it has a slope of negative 1. So that pictured from here, go ahead and down 1 over 1. So it'd be headed towards that point right there. Doesn't have to be perfect. So that means if the graph were to go through the point 1, 1, that would be its tangent line. Now let's look at 2, 1. If x is 2 and y is 1, that would be negative 2 over 1 would be negative 2. The point 2, 1, if the graph were to go through that, then it would be like down 2 over 1. So if you imagine the point right here, it would be headed that way. So again, these don't have to be perfect, as long as you can tell their relative steepness in relation to each other. So you should be able to tell that this one is steeper than this one because it's slope negative 2 versus negative 1. And then let's try 0.12. Well, if x is 1 and y is 2, that would give you a slope of negative 1/2. So at the point 1, 2, the slope of negative 1/2 would be like down 1, right 2, so like headed towards this point. So yeah, it doesn't have to be perfect, but you should be able to tell this one's not as steep as this one. Yeah, let's finish off the first quadrant there. Yeah, point 2, 2. You plug a 2 for x, 2 for y, you get negative 2 over 2, it's negative 1 also. So this one, just like 1, 1, should have a slope of negative 1. So it should run parallel to this line right there. Then we finish the first quadrant. You could do this like for all the remaining points, just one at a time like this. However, it's usually easier. A lot of times there'll be patterns you can use to help you so you don't have to follow each one. So let's think about what would happen if we take these points and if we just switch the x coordinate. We look at the second quadrant over here. So over here, the only difference is the x coordinate is the opposite side. So just think if the x coordinate is the opposite side, that's just going to make it the opposite sign here because it's going to cancel out that negative, right? So here the slope, at the point 1, 1, the slope is negative 1. So the corresponding point over here, when the x is the negative 1, it's just going to make it a slope of positive 1. So up 1 over 1 and towards up 1. Similarly, this one, point 2, 1 had a slope of negative 2. The opposite, so slope of positive 2 would be like up 2 over 1. Then this one had a slope of negative 1/2. So over here, add 1, negative 1, 2 is going to have a slope of positive 1. So up 1 over 2. And finally, this one also had a slope of negative 1. So I'll rub this one. Now, let's see if we can do the same thing over here. On this one, when the y coordinate is just the opposite sign, 1, 1 versus 1, negative 1, the same thing would happen. If the y coordinate is the opposite, it's just going to make it the derivative of the slope of the opposite sign also. So here, the slope was negative 1, so here it's going to be positive 1, so not 1 over 1, headed towards that point. And here the slope is negative 2, so here's going to be positive 2, so up 2 over 1, headed towards that point. Here the slope was negative 1/2, so here it's going to be positive 1/2. So up 1 over 2, headed towards that point there. And this one had a slope of negative 1, so here it's going to be the slope of positive 1, so 1 over 1. And we can finish off the final quadrant here. I say we can either go from either direction. If you change the y coordinate, it's going to make it the opposite. Sorry, if you change the x coordinate like this, it's going to make it the opposite. If you change the y coordinate, it's going to make it the opposite. Either way, you can go from here to here. That's going to be these were positive 1, so it's going to be negative 1. This is positive 1. Negative 1. So negative 1, so down 1 over 1. See this point, this was positive 1/2. So right here would be negative 1/2, so like down 1 over 2. That one there. This one had a slope of positive 2, so here we have a slope of negative 2, so down to 1. And finally, this one is a slope of positive 1, so here's going to be parallel to this slope. Now, it won't always have this kind of symmetry as this one has. It will always be the same type of symmetry across the x and y axis. But we're starting out with a simple one. Now, let me show you what this is really giving you by looking at something else. You see. Remember, to get back to the original equation, what you'd have to do first is separate the variables. So you get the y's with the dy and the x's with the dx. So what you can do is cross multiply there. And that would give you y dy equals, you can put the negative with either one, negative x dx. And cross multiply in this case does simplify, does separate the variables already. And then you can just integrate both sides. And now I give you y squared over 2 equals negative x squared over 2 plus c. And this one we don't have a specific point we don't go through, so we won't be able to figure out the constant. What you can do though is you can add over, normally you'd solve for y, but to show you why we got this slope field, I'm going to do something a little different. I'm going to add over the x squared over 2, and then multiply it all by 2, give you x squared plus y squared plus, equals. Let's take out the plus sign instead of the equal sign next time. Equals c, x squared plus y squared equals 2c. So if you look at this equation here, you might remember this is the standard form for a circle, x squared plus y squared, same coefficient, positive. Circle with a center 0, 0. And remember, this normally in the circle equation is the radius squared, and this is just a constant. So depending on what that c is, will determine how big the circle is. So if you look back at our slope field, you can see this shows us kind of the different circles we could end up getting if we showed you the tangent. So it kind of should give you the shape of all the possible graphs at once. And the reason why now we can see why there wasn't a point here at 0, 0 is because if you had, the only way the circle could go through there is if the constant here was 0. If that's 0, your radius would be 0. You wouldn't actually have a circle, you'd have just a point. If you have a point all by itself, it doesn't have a tangent on it. So that's why there's nothing drawn there. So what I'm going to do at the very end there is actually just erase that, because that doesn't really go in the slope. It was just a reminder not to draw anything there, so that we didn't accidentally put a tangent on it. Now let's take a look at some of the different questions you could be asked regarding this slope field. So the next part says, describe all the points in the xy plane for which the slopes are positive. So basically we want dy dx to be greater than 0. So if we look back at the equation, in order for this to be positive, greater than 0, what would have to be true? Well, one of these, either the x or the y, would have to be negative, right? Less than 0. Cancel out this negative, and the other one would have to be positive. So the way you can say that is all points such that x is greater than 0 and y is less than 0. That's one possibility. X is coordinates positive, y coordinates negative. Or the other possibility is x is less than 0 and y is greater than 0. So x is negative and y is positive. So one of them must be negative. Next part says, over here, describe all the points in the xy plane for which the slopes are negative. If the slopes are negative, that would mean the derivative gives you the slope would have to be less than 0. So in order to make it less than 0, we look back at our equation here. There's two possibilities. Either they're both positive, x and y, which will lead to negative, or they're both negative, so those negatives will cancel. So the way you can say that is all points such that they're both positive, x is greater than 0 and y is greater than 0. Or x is less than 0 and y is less than 0. Then describe all the points in the xy plane for which there's a horizontal tangent. So with a horizontal tangent line, that means the derivative equals 0. So the numerator has to be 0. So if we look back here, that's like when we had 0 over n there. Remember what that has to be true is the numerator has to be 0. So say start with all points such that the numerator, which is x equals 0. However, there's one more thing we have to say. It was true unless the denominator was 0. Then we got that indeterminate. All these points are x is 0 except for that one. So we want to make sure the denominator is not 0. So all points with that x equals 0 and y is not equal to 0. So when it's saying all the points in the xy plane, we're talking about the entire slope. We only drew a small part of it. Then describe all the points in the xy plane for which is a vertical tangent line. With a vertical tangent line, that means the derivative is undefined. So that means the denominator would have to be 0. So to make the denominator 0, y would have to be 0. So you could say all points such that y equals 0. But this time, you want to make sure the numerator is not 0. Because again, if you get 0 over 0, that's indeterminate. All points such that y equals 0 and the numerator, which is x, does not equal 0. And then the next part says, let y equals f of x be the particular solution to this differential equation with this additional condition. Notice the wording of this is very similar to other ones you've seen, except it doesn't say find the particular solution, it just said let it be the particular solution. And what we're trying to figure out is just an equation for the line tangent, for the tangent line to the graph at x equals -2. So that's what our objective is here, equation for the tangent line. So the two things, remember, you need for the equation of the tangent line are your point of tangency and the slope. So we can see right here, this initial condition, that means the graph goes to the point -2, 1. So there is our point of tangency. And we want to write out x equals -2. And then to get the slope, all you have to do, well, the derivative is the slope. So if we go back here, dy dx is negative x over y. So we want to evaluate that specifically when x equals -2 at the point -2 and when y is 1. When we do that, we're negative. X is -2, and y is 1. You can see the negatives cancel out there. And we just get 2 over 1, which is 2. So there's your slope of the tangent. And that's all you need to write the equation of the tangent line. The tangent line would be y minus the y coordinate 1 equals the slope, which is 2, as x minus the x part is -2, so plus 2. And there's your tangent. And then remember to use the tangent line found above to approximate f of -2.1. All you have to do there is substitute in -2.1 into the tangent line. So that would give you y minus 1 equals 2 times -2.1 plus 2. And then you just have to simplify it and solve for y. So we have y minus 1 equals 2 times -2.1 plus 2, it's -0.1. Multiply those together, gives you y minus 1 equals -0.2. And then add the 1. Y equals 1 minus 0.2. So that's what f of negative 2.1 implies. That's the actual point of the tangent, which is close to where the function is. So f of negative 2.1 is approximately equal to okay, let's take a look at, one other thing to mention. Remember, we didn't ask about this. If you needed to know whether this was an under or over approximation, remember that would be based on the concavity. So what we'd have to do is find the second derivative, start with the first derivative, and substitute our point to see if it's concave up or concave down. Because if it was concave down, then our tangent line approximation would over approximation. But if it's concave up, then the tangent line approximate. Just a refresher on that word, we're not asked for it on this one. All right, let's take a look at another one where it's a little bit more complicated. So draw a slope field for the given differential equation to f of points indicated on there. So not as many points this time. So again, the key things to look for are what makes your numerator 0 and what makes the denominator 0. Well, this time what makes the numerator 0 is y equals 1 and the denominator is x equals 0. So let's go ahead and substitute in our points here. So the x coordinate is 0. So we plug in y is 1 and x is 0. Again, that's going to give you the 0 over 0, which is indeterminate. So this time it's at the point 0, 1, right here. That's where we're not going to draw any tangent line. That means the graph would never go through there. Or if it did go through that point, it wouldn't have a tangent where it would not exist. So let's try out the other cases now. Let's try when the numerator y is 1, that makes the numerator 0, and x is not 0. So that would give you 0 over something that's not 0, which equals 0. So again, that's when you have a horizontal tangent. So at the point y is 1 and x is not 0, you have horizontal tangent lines along these points except for right there. And then let's go look at the other way around. What if the denominator is 0, so x is 0, and the y coordinate is not 1? Well, then you get some number that's not 0 in the numerator over 0, which is undefined. And that's when you have a vertical angle. So when x is 0, and when y is not 1, so right here, except for this point, you'd have a vertical. Yeah. So sometimes when it's right on the axis, it's kind of hard to see. So right on top of the point. And again, now we just have to fill in the other points here. So I'm going to start in the first quadrant. So let's start. We already got these points. Let's say we go 1, 2. So x is 1 and y is 2. And if y is 2, that would be negative 1 over x is 1 squared, so you get negative 1. So at the point 1, 2, you'd have a slope of negative 1. So it would be down 1 over. Now let's take a look at the point 2, 2. So when y is 2, you get negative 1 over, when x is 2, 2 squared would give you 4. That would be negative 1/4. So right here at the point 2, 2 would be down 1 over 4. And what's the other point way over here? And on this one, can't really use any symmetry on these points because it's not across the x-axis in a sense. So let's just plug them in one at a time and see what we get here. So if we plug in 1, 0, if x is, y is 0, you get 1 on the numerator, x is 1, on 1, you do get 1. So it's just kind of a symmetry slope of 1, up 1 over 1, except it's across this line. It's like and let's look at 2, 0. So 2, 0, y is 0, you're going to get 1 on the numerator. If x is 2, 2 squared gives you 4 on the number, so 1 point. So 2, 0, you'd have so 1 foot up 1 over 4. So not very steep. Now let's look at across the y-axis here. All that's happening if you go from here to here is the x-coordinates changing sign, from like 1 to -1. So if x-coordinate change sign, look back at our equation here. Notice the x is squared. If you square 1 or -1, isn't that going to give you the same thing? So in this case, it's not the opposite sign across this, it's the exact same thing. So this has a slope of -1. So the point 1, -1, 2 is also going to have a slope of -1. So down 1 over 1, headed towards that point. And this one has a slope of positive 1. So at the point -1, 0, it's also going to have a slope of positive 1 over 1. And again, once you're all done, then you can go ahead and erase that circle that was again, just to remind us not to draw anything right there. Okay, now let's look at some other questions. Again, they're going to ask about the slope field. So again, describe all the points in the xy plane for which the slopes are positive. Again, the derivative that's greater than 0. So this time it's a little bit different on the equation. In order for the derivative to be greater than 0, well, notice the denominator is squared, so that's usually going to be positive, right? It can't be negative. And the numerator is 1 minus y. So we want to make sure to make this positive that the numerator is also positive. So to do that, we just say, well, 1 minus y would have to be greater than 0. Add the y over, so 1 is greater than y, which is the same as y is less than 1. So the y corner would have to be less than 1. So we can say all points such that y is less than 1. However, there is one thing you have to be careful of on the number. Squaring something makes it positive, so it's only going to be positive on the number except if x is 0. And it'd still be undefined. So x can't be 0 to keep it positive. So you'd say, so y is less than 1 and x is not equal. Now let's describe all the points in the xy plane for which the slopes are negative. So the slope must be negative, that means the derivative or slope would have to be less than 0. So now to be less than 0, well, the denominator can't be negative, because it's squared, so it would have to come from the numerator. So this time the 1 minus y would have to be less than 0. And if you add the 1 over, you get 1 is less than y. Sorry. Yeah, 1 over y. Which is the same thing. If you flip it around saying y is greater than 1. So this would be all points such that y is greater than 1. And again, make sure it's negative. The denominator can't be 0 still. Once at the end of 5. So x minus 0. And then describe all the points in the xy plane for which there is a horizontal tangent line. That would mean the derivative would have to be 0. And we already saw what makes the derivative 0 is when y is 1. But the numerator, the numerator would have to be 0 to make the derivative 0. So that would be where y is 1. So all points such that y equals 1. And again, I want to make sure the denominator is not 0, otherwise we have to find. And x is not equal to 1. Then let's describe all the points in the xy plane for which there's a vertical tangent line. So a vertical tangent line, again, that means the derivative is undefined. So the denominator has to be 0. So that would be when x is 0. You could say all points such that x equals 0. However, the denominator 0 doesn't guarantee it's undefined. It does as long as the numerator is not 0 as well. Then 0 and 0 get the indeterminate form. So I want to make sure the numerator is not 0, so y can't be 1. Y. And again, let's look at finding the particular, or let y equals f of x be the particular solution to this differential equation with the initial condition f of 1 is negative 2. And we again want to write an equation for the tangent line to the graph at x equals 2. So again, remember the two things we need for the tangent line are the point of tangency and the slope. So right here, this means this is the point 1, negative 2. There's our point of tangency. And the derivative gives us our slope, so we want to evaluate the derivative specifically when x is 1 and y is negative 2. Look back at our derivative, it was 1 minus y over x squared. So that would be 1 minus y is negative 2 over x squared. Gives you 3 over 1, so there's 3. So there's the slope. So now we can write the tangent line. Y minus, y coordinate is negative 2. Turns that into a plus 2. Equals, the slope is 3. Times x minus the x coordinate 1. And then to use the tangent line on above to approximate f of 0.9. Remember, all you would do is substitute in f 0.9. Like this. We get y plus 2 equals 3 times 0.9 minus 1. So y plus 2 equals 3 times negative 0.1. So y plus 2, 3 times negative 0.1 is negative 0.3. And if you just subtract the 2, y equals negative 0.3 minus 2 is negative. So that's our approximation. That's the actual point of the tangent line, so f 0.9 is approximately equal to negative 2.3. Now let's take a look at some different ones here. This one says the slope field for the given differential equation right here is shown below. So they give you the slope field. Notice they're drawing it for a lot more points than we did. Because really you could draw the many tangent lines for any point on the graph, as long as you don't have 0 over 0. So this kind of gives you the general shape of all the different possible graphs that would have. This is the derivative. And it says sketch the solution curve that passes through the point 1, negative 1 point. So the solution curve, that's like another way of saying the particular solution. Except instead of separating the variables and integrating to get back to the particular solution, we're just using the slope field to show what a graph of it looks like. Because as you can see, this one's a little more complicated. You wouldn't be able to separate the variables on that for x and y. So, start at your point, negative 1, 1. So negative 1. You know it goes to that one. Put a point right there. And then what you do after that is you follow the flow of the many tangent lines in your slope field. So remember these are tangent lines, so you want to run your graph as parallel as you can to the tangent lines that are nearby. So, not an exact science, but you just follow this along here. Okay, it goes like this. And steeper and steeper. This side. Try to make it parallel. And then just stop it once you get the graph. You don't need to put an arrow because you don't necessarily know what's happening out there. Just once you exit your graph there, the slope of it, you can see it stop there. But then we can go the other way also. So if we follow this one, this curve goes up this way. So it levels off right there. It starts curving down. Up again there, and starts going down. Again, until we exit. So just try to make it again, follow the flow of your new tangent lines, the closest to it. What you want to make sure you don't do is things like this. You don't want to go, okay, oh, there we go. Where you're going perpendicular or through tangent lines like that. That tells you you're going the wrong way. Follow the shape of the space, so they would actually be tangent lines. Alright, let's take a look at another one here. On this one, the starting point is negative 1, negative 2. So negative 1 right here, negative 2. One right there. And this for that one. And then again, just follow the flow of the slope. So it's like this way. This. I'm just trying to keep it as parallel as can to the tangent line, so something like that. Here. Here. Like this. So, somewhat parabola like here. Alongside parabola. So again, what this is the graph of one particular solution. Okay, now let's look at how you can match each slope field with a differential equation you can represent. So you could take this like one point at a time, but the easiest way probably is to identify your horizontal and vertical tangent lines of where those should be. Okay, so if you set the numerator equal to 0, well, that would come from x equals 1. And when the numerator is 0, you should have horizontal tangent lines right there. And then, if the denominator equals 0, which in this case that would be y is 0, you should have vertical. So when x is negative 1, to match it up, there should be horizontal tangent lines, when y is 0, vertical. So when x is 1, you should have horizontal. And there's a horizontal one there, but not everywhere else, so that can't be it. Here when x is 1, horizontal, no, right? Here when x is 1, yeah, those look horizontal. And let's check when y is 0, do we have vertical ones? You can see when y is 0, there's are Or see if it doesn't all the way down. So that would be 3 would match with it. And letter B, you can see what makes the numerator 0. That would be when y is 0. Y coordinate 0, we should have horizontal tangent lines. And we said that the denominator equals 0, x equals negative 2. Should have vertical. So, when y is 0, we should have horizontal lines. Another one, right? Y is 0, another one horizontal. So let's do the horizontal on the project, not top of the axis there. And vertical one when x is negative 2. So, that is B right there. The next one, which you can do to make it a little easier on yourself, is factor it. If you set it equal to 0 and you factor it, you get x times y plus 1. Notice this one doesn't have a denominator, so it's not going to have any vertical ones. And there's two different things that give you horizontal here. When x is 0, and when y is negative 1. For both of those, it should be horizontal. So when x is 0, right here, and when y is negative 1. X is 0, horizontal, and y is negative 1, okay, horizontal, so that is C. And so the one last one, process of elimination, we know let's match up with that one, but let's see y. So we said the numerator equals 0, that would come from y equals 1. And the denominator 2, there's no variables there, right? So that can never be 0. So again, you won't have the vertical ones. Just have horizontal ones, and y is 1. And you can see there are horizontal ones. So oftentimes that's all you need in order to get it to match up. However, if you needed to match up two that have the two different ones that fit, all you have to do is plug in, look for a place where one of them has a positive slope and one has a negative slope at the same point. For instance, let's say we looked at these two graphs here, and we're looking at this point. So here it's positive, here it's negative. So if you plug in the same point into both of them, you should be able to tell which one corresponds to positive or negative slopes. You don't know what to do. And let's look at one last type of question. This time we're matching up the slope field with not the derivative, but with the actual original equation we represent. So just remember, you're doing these, all of these, in a sense, have like an unknown constant on it. Could be 0, but it really could be. Because when we're graphing the slope field, remember it represents all the different possible c values you can have. So the key to these is to see which of these equations, just like our circle one, kind of fit in the shape of the graph, which of these would fit in the slope field. So if you remember what the graphs look like, that so y equals negative x, that would just be a straight line, right? The slope is negative 1. So that should be able to fit in the slope field. Well, that doesn't fit in that. This one? Yeah, it does. And you can see why it's all over the place is because of that plus c, that constant. It could be shifted up or down. It doesn't have to be just like that. So this would be match up with A. And then B, so we've got negative x squared plus c. Well, that would be a parabola that opens down with a negative. So it looks something like this. See which one of those could fit an upside down parabola. This one, that's going up the wrong way. This one, no. This one, yeah. Let's see if that's fit. That would be B. And then y equals e to the x, remember basic exponential graph, goes to the point 0, 1. Curves up like that. So we can see, well, this one, kind of, but not quite there. This one, we can see it goes common shape there. That would be C. And then remember what tangent looks like. Tangent river has all these vertical aspects like that. And it looks like that going through the origin. So you want, now you just keep repeating like that. So you can see that one is a bit. And that concludes the notes on the topic of slope field.